Hey guys, hope you are good. So today I'm gonna teach you mass energy equivalence relation, and I guarantee you that once you understand this topic you are not gonna forget it, at least till your exams. I'm also give you some tricks to remember the derivation and some must remember points in the derivation. So let's start. Suppose if force F displaces a particle through a small distance ds, suppose this is a particle and it travels a small distance ds having force F. So the work done stored by the particle as its kinetic energy. So we have dw equal to dk, right? So dw equal to F into ds. This is our equation number 1, right? Now according to Newton's law of motion in relativistic mechanics, F equal to, force equal to dp upon dt, and we know that momentum is mass into velocity. So putting the value of mv in this, what we will get is F equal to d mv upon dt, and this is our equation number 2. So let me make a line separation here. So according to theory of relativity, mass and velocity both are vary. They both change. So F equal to m into, we will differentiate both of them. So F equal to m dv upon dt plus v dm upon dt, and this is our equation number 3. So from equation 1 and equation 3, dw equal to m dv upon dt plus v dm upon dt into ds. This is, so putting the value of force which we have find from F equal to dp upon dt and putting the formula of P equal to mv in this equation, and then differentiating both of them, and after finding the value of F we have to put that value in this equation, that is equation number 1. So we will get this equation, right? Now moving forward, so dw equal to m dv upon dt into ds plus v dm upon dt into ds, right? So I hope you have no doubt till here. Now moving forward, so dw equal to m dv into ds upon dt, right, plus v dm ds upon dt, right? And point to be remembered, gentlemen, ds upon dt equal to v, right? So we will left with dw equal to m v dv plus v square dm, and this is our equation number 4. Okay, now for relativistic mass m equal to m naught upon 1 minus v square upon c square under root, or we can write it like m equal to, or m naught equal to m into 1 minus v square upon c square under root. So we will use these equations in the coming steps. Okay, so differentiate these equation with respect to m. So let us differentiate these equations. So dm equal to, okay, let me make it more clear. So first of all, write m equal to m naught into 1 minus v square upon c square to the power minus 1 by 2, because under root means 1 by 2 power, and when this power comes in numerator it becomes negative, right? So dm equal to m naught minus 1 by 2 into this 1 minus v square upon c square, 1 minus 1 minus minus 1 by 2 becomes, so gentlemen, minus 1 by 2 minus 1 becomes minus 3 by 2. Now differentiating minus v square upon c square, and we will get minus 2v dv upon c square. Okay, now moving forward, dm equal to m naught v dv, okay, upon c square into 1 minus v square upon c square to the power 3 by 2. When it again comes to the denominator, its power becomes positive. Okay, now let me make a separation here, gentlemen. Okay, from equation 5 we have m equal to, this is our equation number 5, gentlemen, make it. So from equation 5 we have m equal to, sorry, m not equal to m 1 minus v square upon c square, which I already written here. Okay, so dm equal to m 1 minus v square upon c square to the power 1 by 2 v dv upon c square 1 minus v square c square to the power 3 by 2. So what we have done in this step is that we have put the value of m naught in this equation, so we will get this equation, right? Now moving forward, dm becomes mv dv upon c square into c square minus v square upon c square. Okay, and its power become positive 1, because 3 by 2 minus 1 by 2 becomes 1, right? So moving forward, dm equal to mv dv upon c square into minus v square. Okay, because when we take c square common, so they will cancel out each other and we will left with c square minus v square. Okay, so dm into c square minus v square equal to mv dv. Give it a name as equation number A. Okay, so putting the value of mv dv in equation number 4. Okay, and after this dw equal to c square minus v square into dm plus v square dm. Okay, so dw equal to c square dm, because when we open this bracket, v square dm cancel out each other, right? So this is our dw, value of dw. So now integrating both sides, and we know that dw equal to dk. So dk integrating equal to, taking c out because it is a constant, into dm from m0 to m, and we will get k equal to c square m minus m0. So k becomes mc square minus m0 c square. Okay, so we can also write it like k equal to mc square, putting the value of m0, so minus m upon 1 minus v square upon c square under root into c square. So this is also one of the important outcome of this derivation. So finally, gentlemen, we know that total energy is equal to rest energy plus relativistic kinetic energy. So E equal to m0 c square plus m minus m0 c square, which we find here. So E becomes mc square, which we have to prove, right? Because m0 c square cancel out each other and we left with E equal to mc square. So the important points that we have to remember to solve this derivation is, first of all, take a point which is moving with velocity f, have traveled small distance ds. Its work done is stored as a kinetic energy, and we know that work done is f into ds. Now we have to find the value of f. So f equal to dp upon dt, where p is momentum. So momentum is p is mass into velocity. So we have to put this value here and then differentiate this equation. After differentiating this equation, we have to put this value in equation number 1. Then we will get dw's value. Okay, then after that, then we will get dw equal to mv dv plus v square dm. So now we have to find the value of mv dv, and for this we use the relativistic mass relation. After getting this relation, we have to differentiate this relation and find the value of dm, which after that we will get and then we will get the value of mv dv, which is dm c square minus v square, and we put this value in equation number 4. And after that we will get the value of dw, which is equal to c square dm, and then we have to integrate this equation, and finally we will get the value of kinetic energy. And for finding the final outcome of this equation, we know that total energy is rest energy plus relativistic kinetic energy. Putting the value of kinetic energy, we will get the final outcome of this relation, that is equal to mc square. So this is all about this topic, gentlemen. Hope you understand this concept. Please subscribe to my channel, like the video and share among your friends. If you have any suggestion and want any separate topic to be discussed here, do comment below. In our next video, we will learn relativistic relation between energy and momentum. Thank you.